Welcome to the Odom Lab at Northwestern University, where scientists are making ions hold very still using a technique called Doppler cooling.
With Doppler cooling, we use light to remove energy from the trapped ions. And using this technique, we can take our ions from room temperature, which is 300 Kelvin, down to tens of millikelvin. So that's 5 orders of magnitude less in temperature.
We can investigate low temperature chemistry. That's what happens how do chemical reactions proceed when the reactants are barely moving at all.
But how cold is cold? Before finding out what's happening inside the trap, shown here, let's talk about temperature. Say you feel like baking a cherry pie. Put it in the oven, and it bakes at 500 Kelvin, then cools down to room temperature at 293 Kelvin. You put it in the freezer, and it's 273 Kelvin. In outer space, it's even colder. 3 Kelvin to be exact. And with Doppler cooling, we can do even better.
To understand Doppler cooling of our ions, you'll need to know 3 things.
First, how ions are trapped in an electric field. Second, how light can be used to push matter. And third, how the Doppler effect works. We'll start by talking about the simplest element, hydrogen. Hydrogen is composed of a positively charged proton and a negatively charged electron. Add an electron, and the entire atom becomes a negatively charged ion. Remove an electron, and the entire atom becomes a positively charged ion. A charged atom, called an ion, can be trapped in an electric field. Like charges repel, and opposite charges attract. Placed between charged plates, a neutral atom will feel nothing, but a charged atom, or ion, will feel a pull in one direction. Our ion trap uses charge to yank the ions into place. So how can light be used to push matter? Light comes in many forms. In the lab, we use lasers because laser technology allows us to specify the color and direction of the light. We can think of light as a wave or as a particle. Different colors of light correspond to different energies, and atoms subjected to these energies react differently depending on their electronic structure. Let's return to our hydrogen example. For many energies, hydrogen doesn't respond. But for just the right energy of light, the electron becomes excited. And when it falls back to its original state, it releases that energy. The same is true when we think of light as a particle. Now imagine we throw a snowball at a skier. The skier slows down. And if we throw enough snowballs, the skier stops. We'll return to this later. Finally, let's talk about the Doppler effect, which applies to both light and sound. In this example, we'll talk about sound. Say we have an ice cream truck emitting its song. What does a bird flying overhead hear when it approaches and leaves the truck? Different frequencies. Say that's the frequency of the truck. This is what the bird hears when it approaches, a compressed version of that frequency, and this is what it hears when it leaves, lower frequency. Same applies to light, and now we're ready to talk about Doppler cooling. The ions are trapped within an electric field, and we shine a laser on them. We use ions, but we'll talk about the neutral hydrogen atom here, as earlier, for simplicity. Within the trap, the atoms are bouncing around. They're just like the bird flying by the truck. They see different colors of laser light depending on the direction they're moving. Atoms that are moving away from the laser source see a longer frequency. But an atom moving towards the laser source sees just the right frequency to excite its electron, absorbing the energy. Remember the skier? When we think about light as a particle, the particle is that laser light, and the skier is that atom. Eventually, all the atoms within the trap are slowed down, just like the skier absorbing the snowball. And that's how Doppler cooling works.
The ions, once they're cool, stay very well localized in their position. This is really great for us in terms of imaging our crystal because while we have our camera exposed, the ions aren't moving in their position, so we don't get any blurring of the light from the ions moving while the camera is open.
Since you have these ions standing almost completely still in the trap, you can study them. You can study their fundamental properties better than you can in any other environment. And one thing we can do with that is look for new physics that we have yet to discover that would be very exciting. Another application of our ion traps would be to make quantum computers. You can use quantum mechanics to process pieces of information in a highly parallel way that's not allowed with classical physics. And our ion traps are possibly a way that people might make these quantum computers and solve some very hard problems which classical computers cannot solve. So we can look at low temperature chemistry, we can make a quantum computer perhaps, we can look for new physics, and that's only a partial list. There are several other interesting applications which you can achieve if you are able to exploit this fantastic environment of ions locked in place and barely moving at all, held in our ion traps, and Doppler cooled, of course.
This video project was sponsored by the National Science Foundation.